Hello there, Matayom 3, grade 9 students. How are you there? Okay, welcome to our next topic, which is now science, but this is chapter 7 on light, specifically topic 7.3, lenses and light. Okay, I'm recording this so that you can review this using your translation in Thai, and then you can review this as many times as you can for your final test. So this is about lenses and light. Optical lenses are made of transparent materials such as glass and plastic with curved sides. Okay? As a ray of light enters a lens, it is refracted. It is refracted again when it leaves the lens. The light rays are refracted in such a way that they form images. There are two main types of lenses as shown below. We have the convex or converging lenses, thicker at the center. And we have another one, the plano-convex lens. And we have the concavo-convex lens. Just see them in the picture here. The concave or diverging lenses means thinner at the center. This is biconcave lens. It means bi means two. There are two sides which are concave. And we have plano-concave lens. One is flat, the other one is concave. And we have here convexo-concave lens because outside here on the right side is the convex, but here in the left is concave. Now, here is the principal axis of this convex lens, and the middle is the center, the optical center. And so we have the rays coming through it, and this is the focal point, which is F, focal point, and the parallel rays passing through a convex lens, it converge at the focal point. So for a convex lens, light rays that are parallel, 1, 2, 3, 4, 5, and close to the principal axis are refracted inward, okay, and converge to a focal point, F, after passing through the lens. And so the thicker the lens is at the center, the shorter is the focal point of the lens. This one becomes shorter. So the thicker, it becomes thicker, it becomes shorter and shorter. Now what about this concave lens? So we see the parallel rays passing through a concave lens, all right? So what happens? They go back right here. They are refracted. So for a concave lens, light rays that are parallel, 1, 2, 3, 4, 5, and close to the principal axis are refracted outwards. Okay, they're refracted outwards here and appear to diverge from the focal point. You see that diverging? After the passing through or after passing through the lens. So the thinner the lens is at the center, the shorter is the focal point of the lens, this focal point. So the thinner this one becomes shorter. So this is the length. All right, and the focal point or F is a common point on the principal axis where all rays that are close and parallel to the principal axis converge to it after passing through a convex lens or appear to diverge from it after passing through a concave lens. So the focal point or the focal length F of a lens is the distance between the focal point and the optical center of the lens. Steps to draw a ray diagram for a convex lens. Step 1. Draw a line as the principal axis and curved lines as the as the convex lens. What to do next? Mark the positions of the optical center, the focal point F and the 2F. And then draw an arrow as the object of standing upright on the principal axis at the given distance. Okay? Here is the given distance, object distance. And then step 4, draw a ray coming from the top of the object. This one, parallel to the principal axis and passing through the focal point F on the opposite side. And draw a ray coming from the top of the object, passing through the optical center in the line, in a straight line. And then draw a ray from the top of the object, passing through the focal point F on the object side. The ray becomes parallel to the principal axis on the opposite side. All right? Step 7, draw the image of the arrow with its tail on the axis. The head of the arrow is the point where the refracted rays meet. Look at that, right? Okay? The image is real. Now, hot tips. Always draw the 3 important rays when constructing any ray diagrams. The characteristics of the image formed by convex lens vary depending on the object distance. The table below shows the characteristics and the positions of the image formed by a convex lens. So we have here the object distance, that is U, ray diagram, image distance, that is V, and characteristics. So at infinite, this object distance, we have the U is infinity here. This is the sign of infinity. We see parallel rays from distant object. Okay? And the image is right here. All right? I want you to see that. At F and on the opposite side of the lens, this is the image. Okay? And the character here, we have the V is F, equals F. An image is real, inverted and diminished. And it's used in object lens of a telescope. All right? What about if it is beyond 2F? So we have here the object distance is more than 2F. And we have this ray diagram as you see in your screen right here. The image is also here. This is the diagram. Okay, try to understand that. And between F and 2F is the image distance. This one. Between F and 2F. Right here. And on the opposite side of the lens. This is the opposite side. This is another side of the lens. So F is less than and even V less than 2F. Right? Okay? Right here. So image is real, inverted, and diminished. And then it's used in single lens camera. All right. So what about if at 2F, we have the object distance, it's called the 2F. So the diagram here is like this. All right, 2F, F, we have another one on the opposite side. Okay, the image is right here. So U, 2F, V equals to F. So at 2F, okay, and on the opposite side of the lens, this is 2F. On the opposite side of the lens, the image distance, that is V. Remember, V means image distance. Okay, this is the object distance. This is the image distance. So characteristic of this is image is real, inverted and same size as the object. All right. So used in photocopier to make equal sized copy. Okay, when you use a photocopy. Now between F and 2F, what is between F and 2F? What is here? Now we have the object distance is less than the here, less than the this part. And as you see, the image distance, this is the object distance, image distance is okay beyond 2F right here. And on the opposite side of this opposite side of the lens. All right. Now you see, I want you to look at the difference between the two. And the distance or the image distance is here beyond or more than 2F because this is 2F beyond 2F. All right. And then image is real also inverted and magnified, you know. So it's used in projector photograph enlarger. All right. What about at F? So the object distance equals to F and the ray diagram should be like this. Okay, object distance, image at where? Infinity. Okay, try to understand the parallels goes through parallel rays, I should say, parallel rays, parallel rays. At infinity, here, the image distance is infinity. All right, okay, and image is virtual, upright, and magnified. Okay, and then use in light beam. You know light beam? Right. What about between F and C for the object distance? What is between F and C for the object distance? So here, the F is equals, I mean, the object distance is equals, is less than F. Because this is F less than F or before. Yeah, here. And so, look at this is the one. All right, less than F. All right. U, or we call the object distance less than F, this one, right? And then the image distance is behind the object and on the same side of the lens. The image distance behind the object right here and on the side of the lens. All right? So this is the side of the lens. And then we have the V, or the image distance is equals to F, right? Look at that. No. The object distance actually we call, I mean the image of distance, which is the V, is right here. Okay. V and the F. Yes. Right here. Now image is virtual in this case and magnified. Used in magnifying glasses. Now, let's understand this figure. The figure shows the three rays in the constructing ray diagram of a concave lens. 1, 2, 3. What happens? Okay. So we have for all positions an object right here. So the image formed by a concave lens is on the same side of the object. Remember, this is the object plus here, object part. And between the object and the lens, between the object, this is the object and the lens. In between right here, the image is formed here. So the image formed regardless of distance, object is always virtual, upright, and diminished. Okay? Now, common mistakes. The focal point, I should say, the focal length, object distance, and image distance. are measured from the edge of the lens, remember? So, this is a common mistake. This is a edge of the lens, the focal point, remember? So, the truth is that the focal point, I should say, the focal length, all right? Object distance, this is object distance right here. And image distance, the image distance that is formed right here. Sometimes the image is on the other side, the one that we already showed in the previous pages. Now, are measured from the optical center C of the lens, from the optical center C of the lens, all right? Okay. Now, applications of lenses, magnifying glasses. If an object is placed between the focal point, all right, F and a convex lens, a magnified upright virtual image is produced. So the image can only be seen by looking through lens, and it appears on the same side of the lens as the object. All right, when you see like this, object. This is how a magnifying glass works. So image of an object is highly magnified and on the same side of the object. This is the object, the image is right here on the same side. This is another side. This is on the same side. All right, is it clear? So, what about the eyeglasses? Now we have the focus on the distant object. The lens is pulled thin. We have the rays here coming through your lens right here. The focal point is right here. The image is formed here at the focal point. And to focus on a near object, okay, the lens becomes thicker. Okay, your lens adjusts. All right, so your eyes will adjust. Look at the other one; it becomes like this. So looking at the near object, your lens will look like this. You see how wonderful our eyes are, so that you have the object form, the image formed here. Okay, so for a person with normal vision, the thickness of the lens is changed so that light rays from the objects are focused exactly on the retina. This side is the retina. So it should be right here, okay? For a normal person, you adjust the lens and the image will be formed at the retina. The images are produced, the images produced are clear and sharp right here in the retina. However, for a person with defective vision, like me, light rays from the object, like this light rays, are not focused exactly on the retina, forming blurred images. So if the focal point here is focused somewhere right here, not in the retina, the image is blurred. That is why now I see blurred images. Like for example, today, I forgot my reading glass at home. So I'm using right now. This is a like for distance driving. So I'm having a hard time and the two eyes are not the same. All right. So one is so blurry, one is not much. So I'm having a hard time reading now. Okay, so there are two types of common vision defects. They are myopia, short-sightedness. So this is mine, short-sighted. It means I see clearly the short distant objects, but I don't see far. The other one is hypermetropia, long-sightedness. These people cannot see clearly the near objects, but they can see the far objects. Okay, hypermetropia and myopia. So most of the people are actually myopic, having myopia. Now, so the eyeglasses here, the type myopia and hypermetropia, we compare them. Here's the condition of the vision for myopia. It sees near objects like me clearly, but distant objects blurred. What for the hypermetropia? They see distant objects clear, but near objects blurred. What are the causes? Here, For myopia, the eye lenses are too thick or eyeballs are too long. All right. For the hypermetropia, eye lenses are too thin or eyeballs are too short. Okay, focusing of light. Light from a distant objects is focused on in front of the retina. All right, this is the retina, right? Where the image should be formed clearly. What happens? The image is formed right here because the light is focused in front of the retina. That's why the image is blurred. For the hypermetropia, light from the near object, this is the near objects, is focused on the behind the retina. This is the retina, but it's behind. What happens? The image on the retina is blurred and light is focused behind the retina. The retina is here. Okay? So both people having myopia and hypermetropia, they see images blurred depending on the distance of the image. Okay? So myopia, uh, they see the image, the distant or far image blurred, but the clear or the near image clearer. For hypermetropia, these people see the distant image clearly, but the near or close objects, they see it as blurred. All right. So how to correct that? If you're a doctor, an eye doctor, corrected the myopia, those who can see near objects, they can be corrected by wearing glasses with concave lenses to diverge. To diverge. Look at that. To diverge light before it enters the eyes. Okay, from here is diverge. Remember diverge, like it goes out rather than inside. So thus, light can be focused exactly on the retina. For the hypermetropia, how to correct their eyes? Corrected by wearing glasses with convex lenses to converge. Look at that. To converge. Okay, it should be focusing on right here. To converge light before it enters the eyes. Look at that, right? You see, compare between the myopia and hypermetropia. This is converging, this is diverging image. Okay? So thus light can be focused on exactly on the retina. Now, refracting telescopes. Refracting telescopes are used to view very distant objects. They use lenses to bend the light from a far object to a specific focal point that the image is magnified to the viewer. They have two lenses, the objective lens and the eyepiece. The objective lens focuses the light to the focal point of the lens. This point is also the focal point of the more powerful eyepiece. The eyepiece produces a magnified image of the image from the objective lens, which the viewer can see. So here, refracting telescope, this is how you see it. And this is the object, parallel rays from a distant object now pass through the object lens, which is convex, right? So what happens? You see it from your eyes right here. Okay? So that's refracting telescope. All right? I want you to understand that more. It's fun in your book, but if you want to take longer time to understand this, you can pause the video and try to understand what it means. So compound microscopes are used to view near and very small objects. A compound microscope is made up of two powerful convex lenses, the objective lens and the eyepiece. The more powerful objective lens produces a magnified image. The eyepiece works as a magnifying glass, magnifies the first image produced by the objective lens. So this is the microscope, compound microscope. So the object is right here. And as you see, this is how you see it through using both lenses. We have the bigger lens and the smaller one. So you can focus and magnify it here so you can clearly see the image with the eyepiece or using through the eyepiece. Now, let us watch this one. I want to make sure that you hear the sound. So, wait a bit. I'm going to adjust something here so that it can be actually, seen clearly. I'm not sure if you're seeing it. All right. Okay. So we have it here. Try to hear the sound. All right. Okay. I hope that's clear for all of us to see.
And to understand how these lenses work. Convex lens. Arrange two prisms so that the rectangular rough surfaces are facing each other. The parallel rays incident on the prisms emerge on the other side after refraction and intersect at a point. Insert a few more slabs of rectangular prisms between the two prisms. The parallel rays incident on such an assembly will undergo maximum refraction at its top and bottom. The rays undergo no refraction at the center of the lens. Now, if we arrange two more prisms at the side of this arrangement, then the incident rays emerging from them also converge at the same point. A single piece of glass formed in this fashion is called a convex lens. We can consider these equally curved surfaces of the lens to be small parts of spheres. The center of these spheres is called the center of the curvature of the lens. The radius of the spheres is known as the radius of curvature of the lens. The line joining the center of curvature on both sides of the lens is known as the principal axis, which passes through the optical center of the lens. The light rays parallel to the principal axis and incident on one side of the lens undergo refraction and converge at a point on the principal axis on the other side. This point is called the focal point or focus of the lens. The distance from the optical center of the lens to the focal point is called the focal length of the lens. The focal length of the lens depends on its curvature. Take two lenses of the same diameter, but of different thickness and hence curvature. When the parallel light rays are incident on them, you can observe that the light rays passing through the thick lens undergo more refraction and get converged at a shorter distance, as compared to the thin lens, which causes less refraction. So we can observe that the thick lens has a shorter focal length than the thin lens. The image formed by the convex lens in this case is a real image of an object. The convex lens can focus the light from the sun to a point on the other side of the lens. The concentration of light energy at this point causes the paper to heat up and burn. The lens in a human eye is convex in nature. We should not look at the sun directly, as it can damage our eyes permanently. Hence, we have understood that the rays of light incident on a convex lens get converged on the other side. So it can also be called a converging lens. Let us look at another kind of lens, which diverges the light rays passing through it. Concave lens. Place two prisms with their vertices in contact and arrange a few slabs of rectangular prisms beside each of them. The parallel rays of light falling on such an arrangement refract away from the center. Overall, we can see that the light undergoes divergence and it emerges on the other side. A single piece of glass formed in this fashion, having inward curvature, is called a concave lens. The parallel rays of light incident on the concave lens undergo divergence as they emerge on the other side. If the divergent rays are extended backwards, then they appear to meet at one point on the principal axis on the same side of the object. This point is called the focal point of the concave lens. The sun viewed from a concave lens would appear as a point. If you place a paper at this point, it would not be heated. The image formed in this case is a virtual image. The concave lenses are used to correct short-sightedness in people suffering from myopia. A concave lens is also used in the peepholes of doors to get a minimized image of the person on the other side of the door. To summarize, we have understood that 1. Light rays parallel to the principal axis and incident on one side of the convex lens undergo refraction and converge at a point on the principal axis on the other side. 2. The focal length of thinner lens is greater than that of the thicker lens. 3. A real image produced by a convex lens is formed on the other side of the object. 4. The parallel rays of light incident on a concave lens undergo divergence as they emerge on the other side. And 5. The concave lens produces a virtual image that is an image formed on the same side of the object.
All right, now that we
Lenses.
have seen it, okay, you don't need this workbook, you don't have it. So conclusions right here, there are two types of lenses, convex lenses and concave lenses. A convex lens is the lens that is thicker at its center than at its edge. Parallel light rays that enter it converge, meaning bend towards each other. A concave lens is a lens that is thicker around its edge than its center. Parallel light rays that enter it diverge, meaning bend away from each other. The characteristics of the image formed by a lens vary depending on the types of lenses and the distance of the object from the lens. I wanted to work on this part. All eye lenses are adjusted to focus light rays entering our eyes to make a clear image on the retinas. Visual impairment, that is myopia and hypermetropia, happen when the clear images formed do not fall on the retina. Therefore, lenses are needed to correct them and allowing people to see clearly. Concave lenses are used in eyeglasses that correct myopia. Convex lenses are used to correct hypermetropia. Besides eyeglasses, lenses are used in microscopes, reflecting telescopes, magnifying glasses, and photocopying machines. Now, work on page 141, test yourself 7.3. I want you to answer all the questions there. All right? See you next time.